How does a machine weighing 500,000 kilograms just leave the ground? Take the Airbus A380. Its maximum takeoff weight is 575 tons, roughly the weight of a fully loaded freight train. Common sense says it should stay pinned to the earth. Instead, it climbs to 40,000 feet and cruises across oceans for 15 hours straight. Our instincts tell us this should be impossible. Physics says otherwise. Today, we're breaking down what's really happening when a plane flies. And once you finish this video, I promise you'll never look at a takeoff the same way again. It won't feel like a simple jump into the air, it will feel like a physics miracle. Because every detail you see in modern aviation exists for a reason. It's the result of more than a century of mistakes, failed prototypes, and stubborn engineering aimed at conquering the sky. For a long time, humans weren't flying. We were just drifting in balloons, at the mercy of the wind. That changed in the 19th century when Sir George Cayley realized something game-changing. To fly, you don't just need a wing, you need to separate lift from thrust. Then came Otto Lilienthal, who risked his life in crude gliders just to prove that a curved wing was the secret to grabbing the air. But the real YouTube moment happened in 1903. The Wright brothers proved that a heavy machine could not only take off with an engine, but more importantly, be controlled. That first flight lasted only 12 seconds, shorter than a skippable ad, but it changed everything. Since then, we've gone from wooden props to the Boeing 747 and the Airbus A380. But here's the kicker. Whether it's a 1903 glider or a 500-ton modern giant, the physics have not changed. Flying is still just a high-stakes game of balance. So, in the end, how does a giant block of metal stay up in the air at all? The answer isn't magic. It's a constant tug-of-war between four basic forces. Picture every airplane in flight being pulled by four invisible ropes. First, there is weight, with gravity always trying to drag the plane back down. Fighting directly against it is lift, created by the wings, pushing the plane upward. Then there is thrust from the engines, driving the plane forward. And finally there is drag, the air itself trying to slow it down. The whole secret is balance. Think of it like a moving seesaw. When lift matches weight, the plane holds its altitude. When thrust matches drag, it keeps a steady speed. But the moment that balance shifts, everything changes. Want to climb higher? You need more lift. Want to go faster? You need more thrust. Every smooth movement you see in the sky is really the result of careful control over these four forces. There's no magic here. It's just physics doing its job. Now for the million-dollar question. How can air, something that feels so light and thin, lift an entire flying fortress into the sky? You may have heard the classic explanation. Air traveling over the top has a longer path, so it has to move faster to meet the air below at the same time. It sounds neat and logical, but that's not really true, or at least not the full story. So let's look at what's actually happening. It starts with the shape of the wing. The top is curved, the bottom is flatter. But even more important, the wing is tilted slightly against the oncoming air. Engineers call this the angle of attack. A simple way to feel this for yourself is to stick your hand out of a car window. Hold it flat, and not much happens. Tilt your palm up just a little, and suddenly you feel a strong force pushing your hand upward. So why does a small tilt make the air feel that powerful? Because your hand, or an airplane wing, is doing two things at the same time. First, it creates lower pressure above it. Once your hand tilts, the air rushing over the top moves faster as it flows around the curve. Faster air means lower pressure above, which helps pull the wing upward. At the same time, it also deflects air downward. Your hand pushes into the airflow and forces that air down. And by the basic rule of action and reaction, if you push the air down, the air pushes back up on your hand with an equal force. That combination, Lower pressure above and an upward push from redirecting air below is what keeps 500 tons of metal moving calmly through the clouds. But there's a limit to the power of angle of attack, and it's a serious one. More isn't always better. Lift doesn't keep increasing forever, just because the wing tilts more. If a pilot raises the nose too much, the airflow can't stay attached to the curve of the wing anymore. Picture the airflow like a surfer riding up a slope. If the slope gets too steep, the surfer gets thrown off instead of gliding smoothly along the surface. In aviation, that's called a stall. At that point, the airflow breaks away, the pressure pattern collapses, and lift disappears almost instantly. The airplane isn't really flying anymore. It starts dropping like a stone. That's why controlling the angle of attack is one of the most important jobs a pilot has, because the goal is to keep the airflow locked onto the wings. Now let's talk about the biggest variable of all, speed. In aviation physics, there's an actual formula for lift, but you only need to remember one thing: speed is squared. And that's a huge deal. It means if you go twice as fast, lift goes up 4 times. But on the flip side, if your speed drops in half, you lose 75% of your lift. Think back to that hand out the car window example. If the car's not moving, you don't feel much. But once it speeds up, the air starts slamming into your hand and pushing it upward. An airplane engine works the same way. It doesn't directly lift the plane, it just creates speed. Once the airplane is moving fast enough, it's forcing tons of air to hit the wings every second. The more air the wings can bend downward, the more lift they create. That's why a plane can't just hop off the runway right away. It needs a long run to build speed until lift is finally strong enough to beat weight. So what actually happens during takeoff? It's not as simple as flooring it and going. It's really a race through 3 speed markers. First comes V1, also known as the point of no return. Once the plane hits that speed, even if an engine fails, the pilots have to keep going and take off. At that point, there just isn't enough runway left to stop. The only way to survive is to get off the ground. Next comes VR. That's the moment the pilots pull back and raise the nose. That small change in angle is enough to make lift, surge, and pull hundreds of tons of metal off the runway. Then comes V2, the safety speed. That's the speed that makes sure the plane can still keep climbing steadily even if only one engine is working, instead of falling back down. And if you watch that moment closely, something really interesting is happening. As the speed keeps building, the wings start carrying more and more of the load instead of the wheels. Then, at the limit, lift fully cancels out weight. The airplane doesn't really jump into the air, it simply reaches the point where it doesn't need the ground anymore. Then, why do passenger planes always climb so high, usually around 35,000 feet, or more than 10 kilometers above the ground? The answer comes down to one simple rule: the higher you go, the thinner the air gets, and thinner air lets the plane move more smoothly. You can think of it like running. Running on a sidewalk is easy enough. Running through a swimming pool would wear you out fast because the water resists every move. Lower air works in a similar way. It's thicker, so the plane has to fight harder to push through it. Higher up, the air gets thinner, which lets the plane move faster while burning less fuel. That's one of the reasons airlines save millions of dollars every year. At cruising altitude, the plane reaches a kind of sweet spot. Lift is just enough to balance weight, and thrust is just enough to cancel out drag. Everything becomes so steady that there's no real acceleration happening at all. But pilots still have to stay in a kind of golden speed range. Go too fast, and air friction starts wasting fuel. Go too slow, and the wings have to tilt up more to hang on to the air, and weirdly enough, forcing that extra lift can burn even more fuel than flying fast. And here's one of the coolest details: step climb. A plane usually doesn't stay at one exact altitude for the whole trip. As it burns fuel, it gets lighter. And once that happens, the pilots can move it up to even higher levels, where the air is thinner still. But a plane can't stay fast forever. At some point, it has to slow down to land safely. The problem is, at lower speed, lift drops a lot. So, how does 500 tons of metal avoid falling out of the sky while moving slower and slower for landing? The answer is sitting right outside your window. If you watch during takeoff or landing, the wings start doing something that looks straight out of Transformers. They change shape. The panels at the back swing down, and the ones at the front slide out. In simple terms, this turns the wing into something closer to a giant parachute. It becomes more curved and more spread out, which helps the plane grab as much air as possible and keep enough lift to stay up. The front slots are especially important. They act like little channels that guide stronger airflow up and over the wing, helping the air stay attached even when the plane lifts its nose higher. And if you've ever worried that a plane would just fall if the engines failed, here's a real example. In 2001, an Airbus A380 lost all fuel over the Atlantic and still glided about 120 kilometers before landing safely. The reason is, a plane needs speed to fly, but not necessarily engine power. When the power is gone, the plane becomes more like a bicycle rolling downhill. It trades altitude for forward speed. As long as the nose stays pointed down enough to keep that speed, the wings can still make lift and keep bringing you home. Then, right before the runway, the pilots make one final move called the flare. They gently raise the nose. It's a bit like leaning back when you're running and trying to slow yourself down. Raising the nose turns the wings into a giant air brake, softens the downward drop, and helps the plane settle onto the runway instead of slamming into it. The moment the wheels touch down, panels on top of the wings pop up to kill off the remaining lift and press the plane firmly onto the runway. Then the brakes and reverse thrust take over, bringing the whole beast to a stop and handing the weight fully back to the landing gear. So when you see a giant airplane lift off the ground, I hope it doesn't look like magic anymore. I hope it looks like the beauty of precision. Humans didn't defeat gravity. We simply learned how to turn some of nature's toughest rules into wings of our own. Flight is no longer something only birds get to do. It's what happens when people truly understand how the physical world works. Before we end this video, here's a question that even experts love arguing about. Imagine an airplane sitting on a giant conveyor belt. The moment the plane starts moving forward, the conveyor belt moves backward at exactly the same speed. In that crazy scenario, do you think the plane would still be able to take off, or would it stay stuck in one place forever? Drop your answer and your reasoning in the comments below. I'm telling you now, that argument never really ends. See you in the next video.